Good morning, sir. Good morning, everyone. So today from Group 7, we would like to present about our case study analysis regarding smart waste collection. This is our group. I'm Avanindra Rustandi.
I'm Latif Hazik Ibrahim.
I'm Baran Andhika.
So for the background of the case study, city waste collection trucks often follow fixed routes and schedules. Sometimes bins overflow before collection, while in other areas, bins are collected half empty, leading to inefficiency. Smart bins with sensors can report fill levels in real time. So the problem statement is that we need to design a computational system that schedules and optimizes waste collection. It should consider bin fill levels, truck capacity, distance and route optimization, time constraints, and fuel efficiency. So the goal from this is to develop a system that dynamically determines the most efficient waste collection routes and schedules to reduce operational costs and environmental impact. And the decomposition from the study case is the key variables are the bin locations, bin fill levels in percentages, truck capacity as L, distance between bins, time and fuel cost per kilometer, collection threshold, for example, 90%. And the objectives are to minimize total travel, preventing overflow bins, and to maximize truck efficiency, which means that it is not recommended to collect half-empty bins. And the challenges are some bins fill faster than others and also a limited trunk capacity.
Next is the pattern recognition. So there are several patterns that we can extract from the waste collection, such as if the waste threshold in the bin level exceeds the threshold, for example, 90%, it will be a candidate for collection. And then we also have to check bin levels and collect waste dailies. So we also need to choose the next bin exceeding threshold nearest to the most recent bin. So then we can already get the pattern, which is we start from the depot, we then collect the trash, return to depot, and then repeat. It's like a cycle. The next one is the data representation abstraction. So for example, we have the inputs here. So we have the bin data. So we have 4 bins over here, 1, 2, 3, 4. And we know, for example, this is just an example. So we have the fill percentage, 95, 40, 90, and 20. We also have the volume for each. Then we can also say that the outputs, so which is the bins to collect, and the truck routes and the total distance. As you can see here, this is from depot kilometer. By the way, this is linear, by the way. And the abstraction is we focus on the bin fill and volume, location, truck capacity, and distance. So for this algorithm, we choose greedy algorithm because it will choose the most effective route to select the bins that have reached or exceeded the threshold. And the most efficient route to take the prioritized bins reached or exceeded the threshold. It's in line with our goal to develop a system that dynamically determines the most efficient waste collection routes and schedules to reduce the operational costs and the environmental impact. So we have the flowchart here. So we start from the oval, which is start, which is then next, we list of bins, here with the level, the fill level, the volume and location, truck capacity, and the threshold we have to focus on it's 90%, which is then filtered to the bins, those that are 90% full or more, which is then stored and then selected bins, which is then begin loop for every available truck. So we start to set the starting route remaining capacity equals to full truck capacity, which is then decided. Is there still uncollected bins and does the truck still have space left? If no, then we have to return to depot. But if yes, we could find the nearest bin to the truck's current location, which is then another decision. Does the bin volume within the truck reach? If it's a no, then you might have to go back to the depot again. But if it's a yes, you can add the bin and subtract its volume again, which is then another decision. Is there another truck available? If no, then you would have to return to the depot again just to do it. And if yes, that means it's the end. Or you could just repeat the cycle again.
Pseudocode is more or less the same as about the flowchart, the inputs, which is the bins and the bins fill level, volume, and its distance and truck capacity. The threshold for the bill the trash is 90%. The algorithm is B for bins, and we chose those bins if they equal reach or exceeds the fill threshold. For each truck, the route starts at the depot. We also, for each truck, we check how much capacity is left to the truck by comparing it to the capacity of said truck. We also select bins which if the bins in the whole area is not empty and how much capacity is left in the truck. We also find the selected bins which is nearest to the truck, while route one is the depot, the starting point to the selected bins. Also, if the nearest bin's volume is less than the capacity, then we select those bins to pick up. If the capacity is exceeding, well, we return to the depot, which is the break, and the route appends to depot, and we go. So for the sample, we're gonna use one truck and sorry, three bins, and we are gonna use a random number generator for the values. Okay, for the truck capacity, it's going to be 86. And for the fill percentage on the first bin, 8. And the volume, 68. Distance from depot, 93. 48. Six. 100. Okay, none reaching the fill percentage. 90. Okay, from the random number generated by the random number generator, it seems that the truck can only pick up bin one and two, but we are gonna prioritize still bin number two because the fill percentage is it's more almost empty because we are trying to avoid overflowing bins. The distance is 100, so probably there's an error with this. It should be 0, but 0. Okay, so we're gonna go to bin 2 because then the volume is probably 66, so they only have 20 capacity left. So because we do not have enough capacity to pick up bin number 1, so we only pick up bin number 2 for the day and we return to the depot. That's probably an example, but it is random, so we cannot control the variables.
For the big O notation for this greedy algorithm, for the best case, it would be O and squared. And the best case scenario just means that the initial plan goes smoothly. And so the algorithm checks a few alternatives and stops almost immediately. The total time is mostly just the time spent creating that good initial plan. Meanwhile, the big O notation for the worst case is O n squared multiplied by the maximum time. And the worst case scenario just means that the initial plan goes terribly, and so the algorithm would need to spend more time searching. The algorithm would be forced to run a maximum amount of time for the Tmax iterations, and in each iteration, it performs an expensive search, the O(n) squared, to find an improvement. And the cost of the search is multiplied by the maximum number of times it can run.
Okay, for the summary, this algorithm completes our goal, which is to pick up the nearest full bin until the truck is full. I'm sorry, for the nearest full bin, which reaches the threshold while saving time, fuel, reducing distance, and avoiding collecting half-empty bins. Thank you for listening.